Hello, everybody. So today, Dante, Steven, and I are going to be going over taxicab geometry. Just a brief introduction to what it is, as well as some key differences that you'll see between Euclidean and taxicab geometry. Okay. So first, it was introduced at the start of the 20th century. The main purpose behind building taxicab geometry was actually just to disprove that side angle, side triangle congruence holds in all geometries. Okay. So, what is taxicab geometry? Well, taxicab geometry is really similar to Euclidean geometry. They both lie on the xy plane. However, the main difference is that Euclidean geometry can go through the grid, while taxicab geometry has to go along the grid. Okay, so let's say for example you want to go from point A to point B. So in Euclidean geometry, since you could travel through the grid, you would go directly from point A to point B. In taxicab geometry, you want to imagine kind of that you're driving along a street, okay? You can't go directly through buildings, so you have to go along the streets like this, okay? Now, one key difference that we see as a result of having to take this path is that the shortest distance between 2 points is no longer unique. So, in Euclidean geometry, the shortest path between A and B is this straight line connecting A and B. However, in taxicab geometry, you could go all the way right and then all the way up, or you could go all the way up and all the way right, or you could even go up, right, up, right, up, right. You notice that this is all just a combination of the same amount of rights and ups, just in a different form. So, since you're restricted to different paths, the distance is calculated differently as well, okay? So when Euclidean distance, you see this formula that we've been using the whole semester, the square root of x2 minus x1 squared plus y2 minus y1 squared. In taxicab distance, however, you want to represent it as a difference in x plus a difference in y values, okay? So the distance formula becomes the absolute value of x2 minus x1 plus the absolute value of y2 minus y1. Now we want to show that this is actually a valid metric, because any of us could just place a restriction on Euclidean geometry and say that we created a new geometry. However, it has to be a valid metric. So we're going to use the definition that we've been using the whole semester, the one that's provided by Dr. Vega. We first want to show that the distance between A and B is equal to the distance between B and A. We want to show that distance is always greater than or equal to 0. We want to show that the distance between 2 points is equal to 0 only when A and B are equal to each other, okay? Then we want to show that the distance between A and C is going to be smaller than or equal to the distance between A and B plus the distance between B and C. So we're going to go through these a little quickly. You notice that absolute values are symmetric, so x2 minus x1 is equal to x1 minus x2, and similarly for the y coordinates. So the distance between A and B is actually going to be equal to the distance between B and A. Then you remember that the absolute value for any number x is going to be greater than or equal to 0. So the difference between two numbers is always going to be greater than or equal to 0. So difference is always going to be greater than or equal to 0. Then the third one, remember, it was an if and only if statement that said the distance between A and B is equal to 0 if and only if A and B are equal to each other. So what you do is you assume that the distance is equal to 0. Then using this formula right here about the absolute value, you have that x2 is equal to x1 and y2 is equal to y1. So therefore, A is equal to x1, y1, which is equal to x2, y2, which represents B. Okay? Then going in the backwards direction, you have to assume that A is equal to B. Then A and B are represented by the same x and y coordinates. So for the distance between A and B, you're just subtracting that x coordinate by itself, and similarly, you subtract the y coordinate by itself, which gives you 0. Okay. Then the last one, you want to assume that A, B and C is given by these 3 points up here. So what you want to do is you get the formula for the distance between A and C, and you add x2 and y2 so that you get this formula right here, which is the absolute value of x3 minus x2 plus x2 minus x1 plus the absolute value of y3 minus y2 plus y2 minus y1. Then you use a triangle inequality of absolute values and you reorganize a little bit. So in the end, you have the absolute value of x3 minus x2 plus the absolute value of y3 minus y2 plus the absolute value of x2 minus x1 plus the absolute value of y2 minus y1, which in the end gives you the distance between B and C plus the distance between A and B. So then you have the distance between A and C is smaller than or equal to the distance between B and C plus the distance between A and B. Now we're going to go on to a real world example. So geometry has always been used to simulate real life things. In this scenario, they were using it to explain how fire would spread in the real world. So Caballero was doing these simulations and he noticed that it wasn't accurately measuring the amount of time it would take for fire to spread. So he was able to compare his simulations versus some real world simulations or some real world fire spreads, and he noticed that it was really different. So in this scenario, the line represents how fire spreads. In Euclidean geometry, you have a point A and you have a point B, so fire would spread linearly. However, in real world, this is not true because sometimes there's obstacles in the way. Sometimes the fire looks like it's spreading down and then it picks right back up. Okay. Taxicab geometry, however, is not also consistent because, as we see right here, it's all the way flat, and then all of a sudden the fire is just really big. It doesn't work like that. So Caballero actually tweaked taxicab geometry a little bit. So we have this red line, which is called the extended taxicab distance. This is the one he uses that he feels most accurately represents fire spread simulation. Okay. Now we're going to go on to Stephen, who is going to explain Euclidean versus taxicab.
Hello, my name is Steven Porta. I was introduced earlier by Jaden, and I will be talking about the differences between Euclidean versus taxicab geometry. So, one of the main differences that you saw earlier is that the lines are different, right? And same for the metric that we use to define the distance between the two of them. So, as you know, Euclidean is a straight line from point A to point B, but taxicab geometry has to make some stops and is more of an amalgamation of a lot of lines that comes together to get the distance total, which can be a lot larger than Euclidean distance in this case. Now, the main differences that I will be talking about are unit circle differences, the circles, and then pi. Now, for the unit circle, this is provided right here. The unit circle is more like a rhombus in this case because of the metric that we have defined, right? So it's an absolute value between distance A and point A and point B, which ends up being a straight line, and as you know, is a lot larger than the Euclidean distance because of the way we have defined it. Now, the reason that we use this unit circle is because it comes in handy to solve for pi, which is used for trigonometry and as well for circles. Now, when we want to solve for the angles such as pi over 2, pi over 4, and pi, this changes as we are no longer able to just use trigonometry to perfectly get there, right? So we have to solve it for radians, and the radians that we get from the unit circle in this case are 8. And the reason for that being is because the circumference is 8, because the distance from point A to point D is 2, the distance from point D to point C is 2, distance from point C to point B is 2, and then point B to point A is also 2. Now, when you add up all of that, you get the circumference, which is 8, and we will be using this later to solve for pi. And when we want to solve for the angles such as pi over 4, pi over 2, and pi, we can define them by a distance or radians, in this case, A going counterclockwise. So from D, which is going to be our initial point at 1, 0, going counterclockwise to 0, 1, 1 radian is between A and D, which is pi over 4, which is about 45 degrees if you want to use degrees. And then pi over 2 is at A, which is a perfect right triangle. And then so on, you could do pi over 3 radians, which is pi over, sorry, 3 pi over 2, which is the same thing. And then you could use 4 radians, which gets you the whole pi, which is a straight line, which is at B. Now, as stated above, you could use these to help us find the radians, which we can use in trigonometry, and you could use some of these angles to help you for the triangles. Now, for circles, circles still maintain their main properties of being defined as the set of points centered around the origin with the distance of r. So as we saw in the unit circle, all of them are around the rhombus, and they will keep this property, but although they keep a lot of the properties from Euclidean circles, they do not maintain the shape. Every single circle in Euclidean is a circle, and every single circle in taxicab is more of a rhombus. And if you rotate it, it becomes a square. And one way to think about it is going around your block. Because if you go around the block walking or in a car driving, you cannot walk or drive through all the buildings, and you have to go around them. And because of this, you have to make a lot more stops. So one way of thinking about it is like that. And if you want, you could also think about it as having to go like around the cube. Now, every circle in taxicab geometry is going to be a rhombus. And the size of it will change if you change the radius. So if I use something like 64, it'll grow a lot, like compared to the unicircle, because every single point on the line is going to be 64 meters or 64 feet, whatever metric I'm using to measure it away from the origin point. And if I want to shrink it, I will use something smaller, like half of a foot. I could use something smaller, like centimeters. If I want to use something smaller, I could just use fractions as well. So everything is going to either grow or shrink depending on how we use it. And now we're going to be using this to solve for pi. Now, the unicircle is going to be our circle of reference because it has radius of 1, and we could use the measurement that we know, which is 8 radians for the circumference, and then we could use the formula known as pi is equal to the circumference divided by the diameter. So c is going to be our circumference, and d is going to be the diameter to solve for the taxicab version of pi. Since the unicircle has radius of 1, as we stated above, the diameter is 2r, which is equal to 2. And since the circumference is 8, we just simply remove the variables and replace it with the numbers that we have gotten now. So we have 8 radians divided by 2, which is equal to 4. So pi is equal to 4, as stated above in the unicircle. And this changes when we try to work with shapes such as squares, circles, and triangles, because as we have used pi over 2, we are now defining a new pi, which will help us show congruency or similarities in different ways as well. I will now be passing it over to Dante, who will be speaking about triangle congruency and how it changes depending on the side lengths. Thank you.
Hi, my name is Dante, and I'll be covering the triangle section in Euclidean versus taxicab. Alongside circles, angles, and pi, a final difference between Euclidean and taxicab geometry is how the triangle theorems and axioms for triangle congruency fail in a non-Euclidean metric. The first example we explored is the side angle side axiom, or postulate. Based on the definition from the book Principles of Geometry, this axiom states that any two triangles with two congruent sides and an included congruent angle are congruent to each other. In our figure, we have the right isosceles triangle ABC alongside the same right isosceles triangle A double prime, B double prime, C double prime, which has been rotated 135 degrees clockwise. Since the line AB and the line A double prime, B double prime are congruent, angle A and angle A double prime are congruent, and the line AC and line A double prime, C double prime are congruent, by side angle side, these two triangles are congruent in the Euclidean geometry. However, when we calculate the taxicab distance between A and B versus the distance of A double prime and B double prime, we find that they do not equal each other. The distance between A and B comes out to be 3 units in distance, while the distance between A double prime and B double prime is 4.24 units, and thus the line segments are no longer congruent to each other, and so the side angle side axiom actually fails in the taxicab metric for this reason. Another triangle theorem we explored is the angle side theorem. This theorem states that two triangles are congruent when they have two congruent angles and a congruent side. Using the same figure from previously, we note that the triangles have two congruent base angles, both measuring to be 45 degrees in measure. Alongside this, but recall that from the previous axiom, the reason it failed was because the distance between A and B is not equal to the distance between A double prime and B double prime. And so, once again, this theorem fails to hold in the taxicab metric, as the two distances do not equal each other, and thus both line segments cannot be congruent to each other. The last triangle theorem we decided to cover was the isosceles triangle theorem. This theorem states that in any triangle, any two line segments are congruent to each other if and only if their corresponding base angles are congruent to each other. Using the figure below, we have triangle X, Y, and Z, where the side lengths XZ and YZ have an equal distance of 1.41 units in the Euclidean metric. And thus, by the isosceles triangle theorem, both the base angles, angle X and angle Y, are congruent, which they are. They are both measure of 45 degrees. However, when we measure the distance between x and z using the taxicab metric, we can measure it by going up 1 unit up and 1 unit to the right, which gives us a distance of 2 units between x and z. And from the figure, we can also see that the distance between x and y it measures out to be 2 units, thus their distances are equal, thus they must be congruent line segments. And since they are congruent line segments, this would imply that their corresponding base angles must also be congruent, which would be angle z and angle y. However, from the figure, we can tell that angle z it measures out to be 90 degrees, while angle y measures out to be 45 degrees, which are not equal to each other, and thus the isosceles triangle theorem fails for this reason. One thing we noted was that triangle congruency in the Euclidean geometry relies on equal side lengths or a combination of equal side lengths on top of equal angle measures. However, due to the distance metric of taxicab geometry, the identical parts become insufficient in guaranteeing a congruent triangle, as distance relies on orientation in the taxicab metric.